This was where we stopped in the last time. So we are considering the jury's method, and like I said, this is the arrangement of the table, of the jury table. So you will start with z raised to power 0, then you stop at z raised to power n. Then write down the coefficients of the polynomial, and write down the reverse of the coefficients in the second row. Then for the b, you're going to, this is the construction. On the third row, you write it from b0 to bn minus 1. So n is the order of the polynomial. Then for the fourth row is the reverse of the second of the third row. Then for the fifth row, this is the representation. So from I to 0 to n minus 2. So you're starting at 0, then you are ending at n minus cn minus 2, where n is the order of the polynomial. Then for the sixth row is just a reverse of it. So remember that for the first two rows, it's you're going to stop at an. For the third and fourth row is n minus 1. For the fifth and sixth row is n minus 2. Then if you have a seventh and eighth, it's going to be dn minus 3. And for a 4-order polynomial, you have 3 rows. So if you have a 5-order polynomial, you would have for a 4-order polynomial, you have 3 distinct rows. So here, this 1, 2, and 3. So 3 distinct rows. So if it was a 5th-order polynomial, you have 4 distinct rows. So in the case we are stopping at cn minus at c, but in case you have other order, then definitely there will be a d. So in this case, d is going to be let me call it h. So ch will be so here will be dh, then here will be c, then n minus 2, then c, n minus 2, then c, then h, then h will be from 0 to n minus 3. So this is the construction of the jury's table. And let's use an example. Before we use an example, in order to determine the stability, it's quite different from the Routh table. So having constructed the table, the next thing is you have 3 conditions. The first condition is that you evaluate f of z at z is equal to 1. And if it's greater than 0, the first condition is satisfied. Then you move on to the second condition. You evaluate f of z at z minus 1. If it's greater than 0 when n is even, then you have a condition that is checked. The second condition is checked. And if you evaluate it at z minus 1 when n is odd, and if it is less than 0 when n is odd, that means that the second condition is checked. then you can now move to the third condition. So for the third condition, you are testing for three things. Then you are testing the determinant of A naught. If this determinant is less than an, then you move to the next condition. You check for this determinant and this determinant. If this is less than this, you move to the last subcondition. Then you check for determinant of C naught and determinant of Cn minus 2. And if this C naught is greater than Cn minus 2, then all the conditions are satisfied. Then that means that the system is stable. But if any of this condition is not satisfied, that means that the system is not stable. For instance, you stop here when you have a fourth order polynomial. So you only have three subconditions. Then if it is a fifth order polynomial, then there's going to be another condition, d0, then there will be a d here, then n minus 3. So you continue that way, n minus 3. So depending on the order of the polynomial. And so this is the jury's method. First of all, you construct the table. So you have all these coefficients of A, B, and C. Then after that, you have to test for these three conditions. If all of these conditions are satisfied, then the system is stable. But if one of the condition is violated, one of these three conditions, if it's violated, then that means that the system is unstable. Before we move to an example, just to take note, so if you have a fourth order system, so if n is 4, then you have three distinct rows. Then if n is 5, you have four distinct rows. So it will be from 1 to 8. So that's the way you construct it. So let's do an example so that we can be sure of how to do it. So we use the same example we started with in this class. Then this is the polynomial. So we are using the jury's method to check for the stability. So there's no need of transforming it. We just use this polynomial directly. The first condition is to evaluate f of z when z is equal to 1. So this is the polynomial. In place of z, we're going to write 1. When we evaluated it, we got 2, and 2 is greater than 0. So the first condition is checked. Then we evaluate f of z as z is equal to minus 1. So in place of z, we put minus 1. When we did the evaluation, we got 4. 4 is greater than 0. And remember the second condition. If you evaluate it, if it's greater than 0 when n is even, then that second condition is satisfied. So in this example, is a fourth order polynomial. So n is equal to 4 and 4 is even. So that means that the second condition is checked. Then we need to evaluate, we need to do this evaluation. So we already know A naught and we already know AN. So we need to get B naught and B3 because N is 3 in this example. Then we need to get C naught and C2 in order to do this evaluation. And so now I'm getting B naught. So B naught in this case is this, you need to get the magnitude of this. Remember we're using, for B naught, we're using this equation. So we have A naught here, you have A4 because N is 4, then because K is 0, so N 4 minus 0, so A naught is here, then A4 is here, 4 minus 0 is 4, then K is 0, so you have A naught here. So because we need B naught and we need B3, we need C naught and we need C2. and we need to test in order to be sure if it's stable or not. So we have B naught. We got it as -8. Then we need to do Bn minus 1, which is B3. Then this is it. Then we got 7. We do the determinant of this. Then we need C naught. So from the expression, we're using this now. So in order to get the B coefficients, is the A coefficient you're going to use. In order to get the C coefficient, is the B coefficient you're going to use, and so on and so on. Now we need to get C naught, and it's of this form. And when we calculated it, we got 15. Now we need C2 because we want to test for this if C naught is greater or less than C2. And we arrive at this. So we need B1 and B2. But previously we don't have B1 and B2. So we need to first of all do B1. We need to evaluate B1, which is -5. Then we need to evaluate B2, which is 2. Then after evaluating it, we can put it into this, and we got 19. So for completeness of the table, we already have B naught, we have B1, B2, we have B3, we have C naught, we have C2, so it's remaining C1. So for completeness, in order to complete the table, we evaluate C1 and we got 26. So we'll now test third for the third condition using this tree. We'll now do the test. Now we got A naught as 1, then A4 as 3. And we know that 1 is less than 3. So the condition 3, the first one, is satisfied. We got the modulus, the determinant of B naught as -8, and that of B3 as 7. And -8 is actually less than 7, is not greater than 7. So this condition is not satisfied. So definitely the system is not stable. Then when we check the last condition of condition 3, C naught is 15, then C2 is 19, and definitely 15 is less than 19. Therefore, this condition is not satisfied. So we definitely know that the system is not stable. And this is the jury's table using the question. So this is A naught, A1, A2, A3, A4. So we got this from the question. Then after that, you do the reverse. So 3, 1, -1, -2, and 1. Then we know B naught. We calculated B naught, B1, B2, and B3. So these were the values we got. Then you reverse this row in order to get the fourth row. That's 7, 2, -5, and 8. Then for the C rows, we got C naught, we got it at 15, C1 we got it as 26, and C2 we got it as 19. Then we reverse this row. So we start at 19, then we end at 15. Because this is a fourth order polynomial, so it's just 3 distinct rows, and like 3 distinct rows, but 6 actually, because you need to reverse it after calculating the coefficient. After doing the first row, you need to reverse it. Then this, after doing the one for B naught, you reverse it. Then after doing the one for C naught, you reverse it. So we have 3 distinct rows. Because this is a fourth order polynomial in this example, we have 3 distinct rows. If it was a fifth order polynomial, you need to continue to do D naught, and you need to continue, and there will be a D. There will be a D naught here, and there will be a D1 here. So that is the jury's method. So in the jury's method, you construct the table in this form using this using this representation, then we'll calculate for this. You already have the A naught coefficient from the question. Then you need to calculate the B coefficient, then the C coefficient, the D coefficient, depending on the order of the polynomial. Then after that, you need to test for 3 conditions. And when any of the condition is violated, then you know that the definitely the the system represented by the characteristic equation is unstable. Now we move on to the last method of finding if the characteristic equation of a discrete time system is stable or not. If you have a polynomial in this form, you also need to, we are now on the Raible's method now. So if you have a polynomial on this form, then you need to calculate some coefficients, the k coefficient. So Ka is given by A naught divided by An. Kb is given by Bn minus 1 divided by B naught. Kc is given by Cn minus 2 divided by C naught, where n is the order of the polynomial. Then if to continue, you can have another k coefficient. In this case, is going to be d. So kd will be, kd is going to be d n minus 3 in this case, then d naught. So you continue that way until you have a single, you continue that way until you get to the last point. So when we use an example, we're going to understand much better. Then in order to calculate your B, in the polynomial, you have A naught and An, but you need to calculate the B coefficient. This is the formula you use to calculate the B coefficient. Then you need to calculate the C coefficient, and this is the formula you use to calculate the C coefficient. If you have a higher order, maybe a fifth order, then there will be need for a D coefficient, and so on, like that. So this is the Raible stable. Then you start from Zn to Z raised to power 0. So remember, for the jury's table, you're actually starting from 0 raised to power 0, and we're ending at 0 raised to power n. So they are quite different. Then after that, you have another column. That column is just for the case. For the case you are calculating. Then after writing the first row for the A, then you write the second row for the B, the third row for the C's. You go on until you get to the last row. And for the first row, it depends on the order. So you start from AN, then you end at A naught. For the second row, you start at B naught, and you end at Bn minus 1. So you keep decreasing the where you're going to stop. So for the next row is n minus 2. For the next row is n minus 3. You keep decreasing it until you just have a single coefficient on the last row, and in that last row you are going to stop. So it's quite different from the jury's method. For the jury's method, you're not going to stop at where there's only a single number on the last row. Like if the order of the polynomial is 4, then you just know that it's 3 distinct rows you are going to have. But in the case of the Raible's method, you keep on decreasing where you're going to stop until you get to a point where there's just a single number on the last row. So that's one distinct difference. And another difference is that there's a column for K And this is the formulas you use to calculate the k. And another key difference is how you calculate the b and the c coefficient. So you can have a d coefficient also depending on the order of the polynomial. So if you have um for instance, if we wanted to calculate a d now, it's going to be, so if we wanted to calculate the d, let's say dh, so dh is going to be ch, going to be ch minus kc, then cn minus h, then minus 2, then for h is equal to 0 to n minus 3. So note the difference. So for b, for the b row, this is the standard method. When you get to the c row, remember you are using, for the c, you just need the b coefficient. Then you need kb. Everything you're going to do is going to be in b's, not. Then for the b's, all the things you're going to need is the a's. For the c's, all the things you're going to need is the b, but you are going to stop at n minus 2 for the c, then you stop at n minus 3 for the b's, then for the d's, you keep on reducing where you want to stop. So that's the construction. And after constructing the table, then you will just look at the first column. You look at the first column starting from B0. So you just ignore the A, the A side. So you look at this column and construct an array to that effect. And the number of positive elements in this column indicates the number of roots inside the unit circle. So the number of positive, so if all of these are all positive, so that means that the system is stable, and consequently the number of negative elements you have, it equals to the number of unstable roots. So that's the condition for that's the Raible's criterion. After constructing the table, so look at this, just from B0 to where you stop, where you have just one element on the last row. Then check the number of positive elements, and the number of positive values equals to the number of stable roots or of stable poles, and it's equals to the number of poles you have within the unit circle, while the number of negative elements indicates the number of unstable poles that is present in the system. So we use the same question we did previously for the Routh and the jury's method. And since in this example n is equal to 4, because this is a fourth order polynomial, so n is equal to 4, so you first of all calculate ka. So ka is defined by this. Then a0 is 1, so a0 is 1, then a4 is 3, so our ka is 0.33. Then we get b0. So this is the formula we're using for b0, where I starts from 0 and ends at n minus 1. So we get b0 using that formula. So it reduces to this. So we know A4, we know KA, we know A naught, and we arrive at 2.67. Then we do B1, we got 1.67 using this equation. We do B2 and we got minus 0.67, then B3 minus 2.33. So notice the order. So for B naught, you're using A4 and A naught. For B1, you reduce it to from A4 to A3, then from A naught to A1, but this KA is still the same. For B1 is A2, then A2, then for B3 is A1 and A3. So notice the trend is A4, A3, A2, A1. KA is common to every one of them. Then from A naught, you will increase it to A3. But from here, from A4, you will decrease to A1. And remember, there's no B4. There's no B4. So for the B coefficient, it's going to stop at n minus 1. So n is 4, 4 minus 1 is 3. So you are stopping at 3. For the C, you are stopping at n minus 2. So n is 4, so that means you are stopping at C2. For the D's, you are stopping at n minus 3. So that means you are stopping at D1. Then for E, there's going to be an E. So you are stopping at n minus 4, and that's 0. So it's just E0. So remember, in the table, you are going to keep on repeating it until you only have one element on the last row, and until you only have a single element. So you just have, yeah, you just have just E naught. Yeah. So if it to say it was a fifth order polynomial, there's going to be an f, and that is at the f, that's where you are going to stop. Then to calculate your C naught, you're going to use the CI formula. Then notice the trend: C naught, C1, C2. So B naught, B1, B2. So for the C's, is the B's you are using. But first of all, you need to calculate KB. And KB is just B3 divided by B naught. So this B3 you got here divided by this B naught. And we got minus 0.87. Then we calculate the C's. You're starting from C naught and you are ending at C2. For the B's, you are starting at B naught. You always start at B naught. Then you end at n minus 1, which is 3. You start at 0, you end at n minus 2, which is 2. You start at 0, you end at n minus 3, which is 1. Then finally, start at 0 and n minus 4 is 0. So it's just only one. So one value you will do here. So for the C's, you use, notice the trend. You have B naught, B1, B2, then B3, B2, B1. And when you do the arithmetic, you're going to get these values. The next thing is to calculate C. So notice the formula for C. C is C2 divided by KC is equal to C2 divided by C naught. Then for KB is B3. It's just the last element divided by the first. So because no here we stopped at B3, so it's B3 divided by the first B we calculated. So here we stopped at C2. So KC is going to be C2 divided by C naught. For KD, as you would guess, we started at D1, then we ended at D1, sorry. Then we started at D1. And for the K, there's no need for the KE because you just have one single value here. So you can't have a KE. So notice the trend: C0, C1, then C2, C1. Then this KC is constant. Then we got the values. Then for KD, we got 0.76. Then for E0, we arrived at minus 0.14. So having gotten all these values, remember you are going to stop when you cannot continue anymore, when you just have one single value. Because for 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 the b coefficients, we had b naught, b1, b2, b3. Then we decreased by -1. So for the c's, you have only c naught, c1, c2. For the d's, we decreased by -1. So we had d1 and d naught and d1. Then for the e's, we decreased by 1. So we just have 1. So it's when you get to the last stop and you cannot continue anymore, you stop. So after doing that, you construct the Raible stable. For the Raible stable, so these are the rows. Remember, you are starting from z raised to power -4 and you are ending at z naught. Then there is an additional column k. So this is the ka, kb, kc, and kd. Then this was the value of a4. This is value of a3, a2, a1, and a0. Then for the b's, this is the value of b naught. So this is the value of b naught. So you are starting, after doing this from a4 to a naught, the next row will start from b naught to bn -1. The next one is c naught to cn -1. So you keep on starting from 0 to the end point. But for the first row, you start from a4. You start from the maximum, then you go to a naught. But subsequently, after the first row, you just start from 0, then you end at n-1, n-2, n-3 until you get to the last row. And having gotten all these values, we just put it inside the table. But notice that there is an additional row. There's an additional row. So this was the row for the A coefficient. And this is the row for the B coefficient. This is the row for the C coefficient. This is the row for the D coefficient. And this is the row for the E coefficient. So these sub rows I'm putting is just the evaluation of multiplying KA with A with the A coefficient. So in this case, you are multiplying KB with the B coefficient, and here you're multiplying KC with the C coefficient, and here you're multiplying KD with the D coefficient. So these rows, this row, this row, this row, and this row, they are not really important. It's just there to simplify the calculation, because what this row does is that if you evaluate this row, in order to get the B coefficient, all you just need is to add these two together. So 3, doing the arithmetic of 3 minus 0.33 is 2.67. So 1 plus 0.67 is 1.67. Minus 1 plus 0.33 is minus 0.67. Minus 2 minus 0.33 is 2.33. So since I've already calculated all these coefficients, really I don't need this row, I don't need this row, and I don't need this row here, and I don't need this row here. It's just to show you an alternative way to do it, because within the calculation, I calculated minus KAAI. So this was where I calculated minus, this was where I calculated minus KAAI. So this is it, and this is it. So I've already calculated it. Then for the B's, minus KB, minus KB, minus KB. Then for the D's, minus KCC2 minus KCC1. So I've already done it in this calculation. So if you do this calculation here, there's no point putting these additional rows here. And like I said, this this row is just you add this and this to get this. So subsequently, then for this row, for the C's, you add this and this to get this. You add this and this to get this. You add this and this to get this, to get this. Then for the D's, you add for the D's, so you'd do the addition. So you add this and this to get this. You add this and this to get this. And you add this and this. There's nothing here. So, and I told you that it keeps decreasing. For instance, for the first row, you are going to have a full length, but for the next row, it decreases by 1. Then for the next row, it decreases by 1 again. For the next row, it decreases by 1 again until you have only a single value at the last row. So the addition of this and this is this. I don't need to do this because you are decreasing the rows. So this column, this row I have here, they are really not important, but it's just to simplify things. So if you've gotten all of this, if you've done all this calculation here, there's no need to put in that row. But if you've done all the calculation and if you want to be double sure of your values, then you can also put in those values. So this is A4, this is A3, this is A2, this is A1, and this is A0. And this is B, this is B0, this is B1, this is B2, this is B3, and this is KB. We've already calculated everything up here. And this is C0, C1, and C2. And this is D0 and D1. And this is A0. So you keep decreasing the order until you have only one single element in the last row. Then the stability criterion for Raible is that you look at the first column. So I told you that you're going to ignore this A row. You're going to ignore it. So you only look at 2.67. So I've bolded it 2.67, 0.64, minus 0.33, and minus 0.14. So you look at all of this. Like I said, this row, this row, this row, this row, they are just subsidiaries. They are not needed. It's just to aid the calculation. That was why it was included. So you're going to look at the first column, with the exception of the A column or the A coefficient column, and you have this vector. Then the Raible stability criterion says that the number of positive elements equals to the number of the stable poles, and the number of negative elements equals to the number of unstable poles, or equals to the number of roots or poles you have outside the unit circle. So definitely we add two positive numbers. So that means that we have two stable poles. You have two negative numbers. That means that you have two unstable poles. And definitely for stability, you need all of these to be positive for stability. So since all of these are not positive, that means that the system is unstable. So this is the end of the class. So just a recap, we are studying stability in discrete time. And for continuous time, we know that the system is stable if the real part of the pole is negative. But in the case of the discrete time, you have a unit circle. So in the z plane, now for continuous time, you are the s plane. For discrete time, you are at the z plane. And for stability, you have a unit circle, then the poles should be within the unit circle. So here is +1, here is -1, here is +1, and here is -1. So if you have the real part of z at 0.8, which is where my cursor is, and you have the real part, the imaginary part at 0.8, when these two meet, they're going to meet here, and here is the unstable region. So that means that is unstable. And that is the condition for stability in the Z plane. So the real, you must be within the unit circle. When you have the poles of the system, they must be within the unit circle, and from -1 to +1 here. And that means that this line here, which is the borderline for stability, it translates to a circle in the case of the discrete time. And we studied the different methods from converting from the S-plane to the Z-plane. Then we'll discover that the trapezium rule gave the best approximation, and it also gives the best approximation in terms of translating the stability in the S-plane to the stability in the Z-plane. But the backward rule, when you have a stable system in the S-plane, the system in the Z-plane is also going to be definitely stable, because this region is the region for the backward rule. So it is within the unit circle. But for the forward rectangular rule, a system might be stable in the Z-plane, but this is the boundary, this line, the shaded region is the boundary is given for stability. So which is not, and some of the region is not within the unit circle. So you can have a system, when you use the forward rectangular rule, you can have a system that is stable in the S-plane, but is not stable in the Z-plane, because portions of it may fall outside of the unit circle. Then for higher order polynomials, where we cannot really break down the roots, or where we cannot really break it down into, for instance, if you have a fourth order polynomial, like if you have a second order polynomial, you can easily break it down to get the two poles. But in case you have this form, how do you know if it's stable or not? And we started with the Routh method. And before you can use the Routh method, you have to apply this transformation. And when you apply the transformation, in the case of this question, we arrived at this polynomial. So it is this polynomial you're going to use to construct the Routh table, similarly to what we did in continuous time case in 412. And we know that the for stability, the first column, they have to be the same sign. And if there are sign changes, the number of sign changes equals to the number of unstable roots. So that's the Routh method. The Routh method, there is a transformation required, and sometimes we don't want that. We just want to use the polynomial given to us directly in the Z plane. So we make use of the jury's method. So in the jury's method, this is the construction from Z0 to Zn. Then you write the A coefficient uh, in this order. Then you write it in the second order. Then you calculate the B coefficient. Then you reverse the order. You calculate the C coefficient. You reverse the order. So you keep going depending on the order of the polynomial. If you have a 5-order polynomial, you have 4 distinct rows. If you have a 4-order polynomial, you have 3 distinct rows. Then after constructing the table, so this is how you get B, the B coefficient, the C coefficient, the D coefficient, depending on the order of the polynomial. Then these are the 3 conditions for stability. So you evaluate f of z, which is given in the question. If it's greater than 0, the first condition is checked. You evaluate f of z at z minus 1. If it's greater than 0, and if n is even, for n is even, that means that that condition is checked. But if n is odd and you evaluate f of z as z minus 1, and if that evaluation is less than 0, that means that that condition is checked. Then after that, you do the last condition, the third condition. So you evaluate all of this. And if A naught is less than AN, then it's checked. B naught is greater than BN minus 1, checked. Then C naught is greater than CN minus 1,